everyone, welcome to the batteries and storage session of today's ETP meeting. I'm Julia Payne from the University of St Andrews, and it's a great pleasure for me to welcome up today's first speaker. So we have Albert, who's going to be talking about ADMM-based units and time decomposition for price arbitrage by cooperative price maker electricity storage units. So thank you very much.
So I have to stay here. Okay. Well, thank you very much for. Thank you very much for the invitation and giving me the opportunity to give a talk. Well, Julia has read the title, and this is joint work with Miguel Anjos and James Cruz. So let's get started. One of the key features of power systems is that generation and demand must be kept in very close balance at any time. This requires flexibility in either side, and as we know, decarbonization increases the flexibility needs, mainly because we are introducing non-dispatchable energy sources like wind and solar, and currently flexibility is obtained from fossil fuels, so if we have to take them out, we lose a source of flexibility. There are many green sources of flexibility, and one of them is energy storage. And in this talk, we will look into it. In particular, we're going to look at large-scale energy storage, and for large-scale, we are thinking about pumped hydro kind of scales, not hydrogen scales, but pumped hydro kind of scales, and potentially batteries if they get large enough. More specifically, we are looking into answering the following research question: how should we control multiple price maker electric energy storage units that cooperate for price arbitrage? Let's analyze what we mean by this. By price arbitrage, we mean that the objective of the storage units is to maximize profit by buying electricity when it's cheap and selling it when it's expensive. We consider multiple storage units, so the decisions to be made are not only to decide when to charge or discharge, but also decide which storage units to charge and which storage units to discharge. We assume that the storage units cooperate between each other, so the objective is to maximize the total profit made by the units as if they were owned by a single owner. And finally, a key aspect we want to capture in our research is the fact that the storage units are price makers, meaning that they are large enough so that they have the capabilities to influence electricity prices. For instance, when they buy electricity, they have the capability to buy such large amounts of electricity that significantly increases the demand for electricity, and that pushes the price per unit of electricity up. I should mention that this work extends previous work on one storage unit by Cruz et al. And our own previous work on 2 storage units. So there's a vast literature in this area, and that links to many aspects of our work. But in the interest of time, I'll just highlight the first 2 works, the one by Graves et al. From 1999 and Sioshansi et al. From 2009, which paved the way to consider energy storage for price arbitrage in deregulated electricity markets. So let's get into the modeling. So first, a convention for us: a positive action means charging a storage unit, and a negative action means discharging a storage unit. And we've said that a key aspect we want to capture is the fact that the storage units are price makers. In the literature, price makers are usually modeled using residual demand curves, which are functions that, given an action of the price maker, they provide the resulting market clearing price after that action has been taken into account. So in a sense, they approximate the market response. In electricity markets, residual demand curves are stepwise monotonically increasing function, where every step represents switching on or off a generator. We won't work directly with residual demand curves, but with what we call cost functions that are essentially the residual demand curve multiplied by the quantity bought or sold. So residual demand curve gives us a price. We multiply it by the quantity, so we have the total cost or reward of doing an action after the marginal price increases due to those actions have been taken into account. So if we take a residual demand curve as the one on the left, and we multiply it by the quantity bought or sold, we get a piecewise linear cost function where the slope of every piece increases as we move to the next piece on the right as the price per unit of electricity increases. Given this property of the slopes, we decided to approximate them by a convex function, and this is what we do. So for us, the cost functions will always be convex. Let's now look at the mathematical formulation of the problem. So consider decision variables x, j, t, that they represent the action taken by storage unit j at time t, and assume that the objective is to minimize the cost over all time periods. Note here that the cost functions are the cost function at time t is evaluated at the cumulative action of the storage units at time t. This is precisely to capture the cooperative aspect of the problem together with the price maker assumption. So the action of one storage unit influences the price that the rest see. Subject to the standard storage units constraints, so at every time step there's a limit on how much we can charge or discharge every storage unit, which we denote by Pj. And the state of charge of the storage unit has to be between 0, representing empty, and the maximum energy capacity of the storage units, Ej. And finally, we also fix the final state of charge to avoid situations where typically the storage units would end up empty by the end of the time scheduling horizon. So just a few remarks on this model. So this is a discrete time model because electricity markets are discrete. And secondly, we are assuming that prices are deterministic, meaning that the storage units have full knowledge of the cost functions. So in particular, they know future electricity prices and how their actions would influence them. This is arguably a strong assumption, but as we shall see later, our solution method aims to exploit a time decomposition that should put a limit on the amount of future price information needed. We will still need some, but not as many as might seem. Okay, so our work mainly proposes a solution method to solve this problem. So let's look into it. This solution method combines a decomposition by storage unit and a decomposition in time. So let's look first at the decomposition by storage unit. So the first observation is that, well, there are n groups of decision variables, one for every storage unit. So we group them by storage unit, the decision variables. And if we fix n minus one of them and we let one of the other variables free, we can obtain n different one-unit subproblems, one for every storage unit, if we change the variables that are being fixed and the variables that are let to optimize. And then once we have all these subproblems, what we proposed is using a solution method called an alternating direction method of multipliers, also known as ADMM, which essentially has the following scheme. So we would solve the subproblems. This gives us incumbent solution X. Then that allows us to update the Lagrange multipliers, and that gets retrofitted into the subproblems which depend on those Lagrange multipliers. And this process is repeated many times until primal feasibility is obtained. In a nutshell, that's quite a schematic. So now moving on to the decomposition in time, the key message is that all the subproblems are one-unit problems. So they potentially have a long time horizon, and a natural question to ask is, well, at every iteration of this loop, do we need to solve all the subproblems until the final time? We propose not doing so, and instead use the time decomposition, an algorithm from the literature by Cruz et al. From 2019, uses to solve one-unit problems, because all the subproblems we obtain are one-unit problems. A key feature of that algorithm is that it uses a decomposition in time that's done on the fly, so while obtaining the optimal solution, and that decomposition does not compromise optimality. So that's for the one-unit case. Of course, in our case, optimality might be compromised, but, well, that's what we have. So how does that, so we have that algorithm that uses this nice decomposition in time. So how do we move it to our setup? Well, we have several of these subproblems that need to be solved simultaneously. And basically, well, if we apply one iteration of that algorithm, we obtain a time decomposition, a first step in the time decomposition for every subproblem. And then what we propose is, well, these are going to be potentially different. And what we do is essentially look at the longest horizon, solve all the subproblems until that time, and then use that to make decisions. So, okay, let's look at the results. So we applied this solution method to a storage unit example, and the results are plotted in this graph. So on the right-hand side, we can see electricity prices from which we build quadratic cost functions. And on the left-hand side, we see the resulting state of charge from obtained by our solution method. At first sight, we see that the solution makes sense because electricity prices have a strong daily pattern, which is matched by the states of charge of the storage units. And also during this week, there were two price spikes, one before hour 48 and one before hour 72. And during those price spikes, the storage units discharge strongly, which is what you would expect if they were to operate for price arbiters. So at first sight, the solution makes sense. Okay. So now if we compare our proposed solution method, which is the third column in this table, with our previous solution method, which is the second column in this table, the first observation is that while both methods are theoretically able to cope with any number of storage units, our previous method had a very nested structure, so we couldn't go beyond 2 storage units. And so this comparison is only for 2 units problem, but as we've seen in the previous slide, we could solve 4 unit problems or beyond. And what we see here is essentially that while the previous method was provided slightly better solutions, in general it was sometimes unstable. Our new method provides the slightly worse solution, but the difference is rather small. But if we look at computational time, we see massive gains. So our previous method took around 100 seconds to solve 1 month instances, whereas our new method takes less than a second. And that's precisely what allows us to go beyond 2 storage units with our proposed solution method. And finally, to conclude, that well, we could, with our new solution method, we could solve instances with more than 2 storage units, which we couldn't do before. We've seen 2 orders of magnitude computational time reduction compared to our previous algorithm into unit instances with small quality losses. And finally, in future work, we aim to relax the convexity assumption we did on cost functions and work directly with the functions that you would obtain from just multiplying the residual demand curve by the quantity bought or sold. Thank you very much for your attention, and here I'll leave the rest.
So thank you very much for a great talk. Does anyone have any questions for Albert? Oh, there's a few here. Job and first.
Hi, quick question. You mentioned that you run the algorithm until primal feasibility is reached.
Yes.
Not an expert. What does it mean?
Okay, so I rocked a few things under the carpet, so I didn't write the full formulations. But essentially, to run the algorithm, okay, maybe I can go back. Yeah, so to run ABMM, this problem has linking constraints. So there are constraints that if you were to separate this problem, since the cost functions on top are not linear, that links the whole constraint. So we introduce new variables that essentially ZT define as what's inside, and that brings us a linking constraint. So that linking constraint is relaxed to be able to then split into problems, and then you solve until that relaxed constraint is satisfied up to your desired tolerance. So that's primal feasibility, because otherwise that's not feasible. Thank you.
Thanks very much. I was just wondering, I maybe missed this, but to what extent are you modelling the current situation versus some future scenario? Do we currently have electricity storage media that are big enough to influence the price? So
this example is with the four largest storage units in the UK. So there's Dinnerwick, which has slightly less than 2 gigawatts of power, so that's quite big. And we believe that those have market power, because they are also very rapid. I mean, they can provide power in terms of seconds, like in 12 seconds they can be. If they do some tricks. It's not always that they can do that, but if they are in the right setup, they can provide power very rapidly, and they are large. So I mean, 2 gigawatts is quite large. The others are not as big, so, but yes, I mean, and maybe in the future there are more to come. So thank you very much.
Was there any more questions?
Hello. Thank you for the presentation. I was thinking, like, do you think it makes any difference, like, if the batteries are not price maker but a price taker? Like, for example, can you extend to the EV or like a smaller batteries? Or is
So-
it much easier program?
If they are price takers, then they are kind of out. If they are all price takers, then the cost function becomes linear, and then you can automatically, because the constraints are already separable. So then you can automatically break, and you have one unit problems.
It's much easier.
So it's only the price maker assumption that makes them interact. So to speak.
I see.
In this model, I mean.
Thanks.
One more question.
Thanks, John Lowe, Edinburgh University. I'm interested in the, and it's maybe a different angle, but if you've got the two or more working together, is that likely to be beneficial for the service provided to the public, to the users, in terms of, is it a cartel? Is it illegal? Is it going to make it more difficult for people to get a fair price? Or does it benefit the price that they have to pay?
That's a very good question. I mean, the bigger you get, the more market power you can exercise. The storage units, I mean, the only way they can exercise market power, so in this case, the price maker assumption is bad for them, because it means that when they buy, that increases their buy price, and when they sell, that decreases their sell price. So the only way, as far as I know, that they can exercise market power is by holding capacity. So saying, compared to the social optimal, I'm just not going to buy or sell as much. And I suppose coming back to your question, whether having them together it's difficult to say. I mean, I don't know. They could exercise market power, yes. But at the same time, if they are able to cooperate, then they can do more to help us. So, I don't have an answer to that. Thank you.
So thanks very much. I think that's all the questions we have for now. So let's thank Albert again. And let's welcome our next speaker, who will be Fraser.
Hello everyone, thanks for coming along to this talk. My name is Fraser McCann. I'm a 5th year chemical engineering student at the University of Strathclyde, and I'm here to present some of the results I got during a summer placement at the university under Dr. Dragos Nigu, and that's his contact details there along with my own. My project was sponsored by the Royal Society of Chemistry, so I'd firstly like to thank them as well. So a bit of background. Many energy conversion technologies like solid oxide cells and electrolyzers rely on oxide ion transport. A conductivity is a measure of the ease of transport of these ions, and therefore an enhanced conductivity means we can store more energy, or in the case of electrolyzers, it can split more water, to make more hydrogen. Current strategies to improve conductivity include doping and crystal lattice engineering. But what we looked at over the summer is looking at endoparticle systems. So these are a new type of material, and we looked at the conductivity of these materials over the summer. So endoparticle systems consist of a host structure, and that's usually a perovskite, which is a metal oxide state-of-the-art ion conductor, and we embed particles within them in the nanometer scale. And previous work that the group found was that by embedding these particles within the host structure, it generates strain throughout the host structure, which leads to a conductivity enhancement. One of the models I carried out was the effective temperature on these systems. I used Arrhenius plots, which are great visual tools for looking at an order of magnitude change in conductivity. So I plotted the log of the conductivity enhancement ratio, which the term on the top of the fraction is the strained conductivity, I like to say. So the conductivity as a result of being strained by endoparticles. And then on the bottom, it's the unstrained conductivity of the original host structure. We looked at 2 state-of-the-art ion conducting materials, YSZ, which is yttria stabilized zirconia, and another lanthanum-based perovskite LSGM. We plotted it against 1/temperature. How I got that ratio, I'm just kind of outlining here quickly. So we went from originally a 2D model and used that to approximate the strain throughout the entire volume. And then that's how we got that there. And then this was based on the previous work by my supervisor and another student. And here are just the results quickly. It's quite a busy slide, so I'll try and take it through slowly. You've got a series of different colors of lines here. The different colors represent particles which induce different strains upon the host material. So we've got black lines which induce a 3% strain. And by that, what we mean is when you line up a particle and the host structure, there's a difference in the way their lattices align. So the greater that difference, the greater the strain. So I've got 3 different percentages of difference, if you will. So 3% in the black, and in the pink 5%, and the green 7%. And then I've also got different types of line as well. So the dashed line represent endoparticles with size of 4 nanometers, and they're loaded at 4%, 4 mole percent. And then we've got dotted lines which represent a size of 7 nanometers and a loading of 12%. And finally, the solid lines represent particles with a diameter of 12 nanometers and a loading of 25%. We also have for reference in the grey, the unstrained host structure conductivity. And the best way to visualize the conductivity enhancement of these materials is by looking at the gap between the unstrained solid grey line and the different strained lines, if you will. So for the 2 different host structures, YSZ on the left and LSGM on the right, the biggest gap seems to occur between the solid grey line and the solid green line. And it seems to be greatest at lower temperatures. It's certainly in the case of LSGM compared to the YSZ, where it seems the gap seems to be a lot more constant. So what I'm trying to say there is there's less to gain, essentially, by changing the temperature in a YSZ endoparticle system compared to a lanthanum-based host structure. And again, just kind of reinforcing those results, I've just got, instead of the log or Arrhenius plot, I've just got the conductivity enhancement against the temperature for both of them. And again, at the lower temperature on the LSGM plot on the right, as you can see, at a lower temperature, the conductivity can be enhanced up to 30 times, which is pretty encouraging because if at lower temperatures, there's lower energy requirements and lower cost. And again, reinforcing that there's less to gain by changing the temperature in the YSZ structure. There's not that much to change, roughly 1.6 to 2.6. So again, this is just kind of summing up what I found. So there's less to gain in a YSZ compared to an LSGM endoparticle system. We want bigger particles, which generate greater strain and at greater loadings. We also found that conductivity enhancement is better at lower temperatures, which is technologically very, very significant. And also, if we're improving upon the state-of-the-art materials, then are endoparticles the future? There were some assumptions in the modelling. For example, a lot of the physical parameters of the different materials, we didn't consider variation of temperature because there just wasn't enough data in the literature. So we could argue that the results are actually conservative. Thank you for listening. Is there any questions?
So thanks, Fraser, for a really interesting talk. Is there any questions? I have some anyway. So I guess I can start off by asking you one question. So I'm really sorry, I still don't quite understand what the endoparticles are. So I understand YSZ, LSGM,
Yeah.
but can you explain a bit more about the
Yeah, so
endoparticles?
the initial model or the initial paper that has been carried out, these systems have been made and they have been done by experiment. And I was kind of continuing on with that. But what I was finding was when I was using YSZ as a host structure instead of the one used in the paper, I was actually getting a compressive strain. So if we're compressing the host structure, then there's less space for ions to move about. So I wasn't getting great results. So essentially what we said, well, okay, if the data's not there for us in the literature, well, let's just make up particles with an arbitrary size that should induce a certain amount of strain. So are you meaning like the materials that they would be, or?
Yeah, I mean, I guess, yeah, that's part of the
So
question.
in the original paper, it was 2 applications, so a solid oxide cell and a chemical looping system, and that was an LNTO perovskite, which is just another perovskite, and that was embedded with nickel oxide. So it's just different metals or metal oxides, and they're produced using different methods, which again is quite technical, using exsolution methods. I don't know if anyone's heard of that, but essentially that they can be fired using sintering or reduced to make them as well.
Yeah, so based on that, I mean, obviously you've looked at YSZ
Yeah.
and the LSGM, so they're 2 families of oxide ion conductors.
Yes.
So obviously there's a few more families of
Yeah,
oxide
yeah.
ion conductors that I can think of. Have you started to think about those and how the conductivity is going to be changed?
So
for
my
those?
project was only 8 weeks, so we were kind of limited to what we could do. The next stage for us would be improving the model to make it a lot more general. We would look at different types of conductivities, different materials for different applications. So that would be kind of the next step, essentially.
That's great. Thank you very much. You've got some questions?
Although not really a question, but it looks like he didn't really get the question you were asking, because in a solid oxide cell, mostly the previous work were looking at the activity on the surface. So our materials, the catalytic activity was only focused on the particles that comes to the surface. So when he's talking about endoparticles, he's also having this particle within the bulk of the material. So I think that was what you were trying to do. Yeah. So that's the question.
Yeah, explained much better than than me, thanks. Yeah, yeah.
Thank you very much for the presentation. Have you got any more information about the strain-induced enhancement of the ionic conductivities of your material? And you mentioned overlapping crystalline lattices, and then you've also mentioned the creation of greater holes in the material. So a few more comments on that, please.
Yeah, so I think I kind of brushed over, I was wary of the time, so I kind of wanted to kind of brush through the model. How it starts is we start here with a kind of 2D here. So we use this equation on the left, and that epsilon I term on the left-hand side equation, that's essentially, we call that the interface strain. So every lattice of different materials, it's quantified by something called a lattice parameter, which my interpretation of it's just to do with the way they're aligned. It's how it's how the layers of the lattice align. So that is just the difference of how, when you connect them, how they are, at what orientation they are aligned, and that's how we quantify that interface strain. And then what the graphs are showing is how that strain varies between 2 different particles.
Okay. So we see the strain varying there, but how does that lead to greater ionic conductance?
So the idea is that if we are stretching this material, be due to this kind of positive interface strain, then that's creating more space for the ions to move around. That's the kind of physical interpretation of it.
Okay, thank you.
think in the interest of time, I think we can move on. But thanks very much again,
Thanks.
Fraser, for an interesting talk. So that brings us to the final speaker of today's session, anyway. And we've got Nagisa from the University of Edinburgh, who's going to talk about pre-trained solution methods for unit commitments. So thanks, Nagisa.
Okay, thank you for having me today. Today, I'd like to talk about my PhD work. I'm a postdoc in Edinburgh University in the School of Maths, but this is like the work I did in my PhD. And Andreas and Ken is my PhD supervisors. Okay, and today I'd like to talk about the solution method to solve unit commitment as fast as possible. So I want to introduce what the problem is, and two of the works I want to explain. So today, the first part, the unit commitment, it's very similar to like problems talked by Albert. It's a scheduling of the power plants. Imagine your power supplier, you have a fixed set of power plants. By the way, I have nothing to do with batteries in this talk, but I was assigned to this session, so please don't worry if you lost. So generators, and we have a given set of time periods, tomorrow, for example, and we are given demand we have to satisfy. And our problem is we want to find out a schedule of the power plants, when to switch on, when to switch off. If we switch on, how much power we want to generate. We want to find a cost-effective schedule in using the optimization. And the problem looks like the one written on the upper part. The one of the most significant part is we have a constraint which binding generators together, but otherwise all the constraints are local to each generator. So the typical approach in optimization literature is like a decomposition using Lagrangian. So Lagrangian deal is defined, or deal function is defined in the lower part. This is Q, which have like, if you optimize it, we get the very close lower bound to the original problem. And this problem have a very nice feature, which is, one feature is which is separable into each generator, which is similar to the Albert's talk. And another very significant part is the function is concave. So we can use like a very efficient solution method, very dedicated for the convex optimization or concave. And here is the demonstration, how to solve the dual function optimization or maximization. Concave means like a mountain displayed on the left or right. And in a cut-and-play method, for example, we iterate, we have an initial guess of the solution, and we evaluate the function value in a gradient value there. And we make a locally valid model, which is one single cut. And we regularize it, and we solve the, we find a maximizer of the regularized model. And we use this as our next guess. And we evaluate the function and the gradient value, update the model. Now we have like two cuts. So we regularize it and solve it, and finding our next guess of the maximizer. So this is like a classic approach to optimize this function. So in my PhD, I try to improve this procedure, how to solve this problem much faster. There's two parts I'm going to talk about today. The one part is how to find the initial guess. So in this picture, Y0, it's better to be close to the optimal, of course. So how to find this good initial value. And next part is, in this picture, I said I iteratively evaluate the function and construct a piecewise linear model. But so next iteration will be evaluating the function value at the Y2. But as we see, the model of Q1 is already very tight. So it seems like evaluating Q1 doesn't look attractive, and we want to maybe skip it and only update model of Q2. But can we do that? We're going to analyze the situation. So the first topic is initialization, how to find a very effective Y0, very near optimal initial point. If we solve unit commitment every day with different demand for tomorrow, what we can think about is maybe we can use like supervised learning. We solve unit commitment with different demand every day. So we gather the data. If the demand is this, our solution, our optimal dual value was this value. So we can solve many, many training instances, and then we can run standard supervised learning. If the demand is this, optimal dual is this, can you make a prediction? This approach is good, very standard, but one downside is this is very sample intense, data intense, which means I have to solve the unique commitment problem many, many times. But solving unique commitment problem is very expensive. We want to avoid, because motivation is we want to speed up the solution process. So this is very slow already. So we need something more efficient. And if we exploit the structure of the dual function or our optimization problem at hand, we can do something more clever. So imagine omega is demand, by the way. So we want to find a network which takes a demand as the input and output the optimal prediction of the optimal dual value. Our goal is on expectation. Whatever demand is given, we want to find a very good dual function value or like a very large dual function value. The dual function is actually separable into generator. So what we can do is we can actually not only sample demand, but also we can sample generator or sub-problems. And we can make the final expression. This is much smaller than the original dual function, because dual function, we have to solve all the generator sub-problems, but last expression only relevant to the single generator. So what we can do is we can use the last expression and run the stochastic gradient descent, not only sampling demand, but also we can sample generator, and we can stochastically update the neural network weight. So this is, I'm gonna skip. So this is quick result. So we are trying to find a dual function, dual value, which maximize the dual function. So if we find an exactly optimal dual value as a prediction, our loss is 0. The value on the table is 0. If our guess is very bad, for example, 0, then our loss is 100%. Our prediction error is 100%. So smaller is better. And we have a different generator, a number of generators, 200, 600, 1,000. The top row is our approach. And a random forest and nearest neighbor is supervised learning. And LPR is something we find in the literature. It doesn't do any learning, but it's like a standard method people use. And cold start is just y equals 0. As we see, our method can output very tight law, very, how do you say, good prediction in a very, very quick time. And then second best is the supervised-based method. And LPR, optimization standard method, is, first of all, the guess is a bit off. The loss is very large, or error is very large. And also they take a certain amount of time because they internally solve some problems. So we find some good method. Given we solve unique commitment many, many times, we can use our method. And if we plug in this and actually run the optimization of the dual function, we actually find a near optimal dual value very quickly. So it's not only finding a good initial point, but it also helps the optimization algorithm. I'm gonna skip this. It's not very relevant. The second part is incremental cutting plane method. As I displayed, the standard cutting plane method evaluate each component, solve all these problems in each iteration. But what if I skip some component evaluation and I only evaluate a subset of the function? What happens? We make some study, and actually we can establish some result. So if we make the regularization constant, then we can say how far we deviate from the actual optimal solution. And we can also say, even if we skip some component evaluation, we can eventually find the optimal dual value by play with the regularization or step size in this slide. This is good as a theoretical study, but also in a practice, we also observed some benefit by skipping some component evaluation. So instead of evaluating and updating all the components, we can incrementally update. This is the experimental result. Different color indicate the strength of the regularization. I haven't mentioned anything this talk, so we can ignore. But the solid line is the full component evaluation, full step method. And the dashed line is the incremental method. We can see if we compare same regularization strength, so apple-to-apple comparison, incremental method finds the optimal solution more quickly than the original traditional full-step method, so empirically we also observe the benefit of only evaluating subset of the function. This is because this is the, probably I'm gonna skip just of the interest of time. So the work is put on the archive and now under review. So if you are interested in, check this draft, and thank you for the listening.
Thanks very much, Nagisa. Thanks for an interesting talk. Does anyone have any questions?
Hi, thanks for the talk. A quick question about the neural network that you use. When you calculate your computational times, does that include the time it takes to train the network? And if not, how long does that actually take? Because in some cases that can kind of negate the whole.
Yes. Yes. So it's actually a very, very good question. And in the time reported in this table, I only reported after training how much to evaluate the network. So it's very quick to evaluate, but as you mentioned, we have to actually run the pre-training phase. In this experiment, we run like a 1 day, like 24 hours training. So in this talk I skipped, but in practice, we have to run some.
And okay, so that sounds perfectly sensible, but is 24 hours okay given the application you're looking at? As in, will the information update quicker than 24 hours, or will you be okay by doing that on a, because you might have to retrain it if information changes, right?
Yeah, it's a very good question. We believe it's a relatively practical setup because we only use, 24 hours and like a small computational resources. So if we are in a company, we can run this computation in a much bigger computer in a much faster computing time. Yeah, thanks.
Thank you.
And one kind of consideration is we also need data. For example, I use the historical demand data, but typically these data are available. Thanks.
Are there any more questions? If not, I think we can just thank everyone in this session again. So thank you all very much. Thank all the speakers very much.